Welcome to Part 2, where we will continue with looking at connectivity in the central office, including patching, termination, and cable management of fiber cords. Let's return to the four basic functional requirements of any fiber distribution system: terminations, splicing, slack storage, and housing of passive optical components. In order for the signal to get from one fiber to another, the cores of the two fibers need to be joined and brought into near-perfect alignment. The measurements that determine the quality of the junction are insertion loss and return loss. Insertion loss, IL, is a measure of the power that is lost through the junction, and a typical loss value of 0.3 dB is equivalent to about 7% of the power being lost. Return loss, RL, is a measure of how much power is reflected back to the source from the junction. A return loss value of 57 dB is equivalent to 0.0002% of the light being reflected back. There are two means of joining fibers in the industry today: connector terminations and splices, and although these have been discussed in an earlier lesson, we will briefly recap. Connector termination in fiber optics refers to the physical joining using a mechanical connector of two separate fibers with the goal of having 100% signal transfer. Connector terminations used for junctions are meant to be easily reconfigurable to allow easy connection and reconnection of fibers. There are several fiber connectors available in the industry today. The most commonly used single-mode types are SC, FC, and LC. Typical single-mode ultra-polish connectors, UPC, will provide insertion loss values of less than 0.3 dB and return loss values of greater than 52 dB, while single-mode angled physical contact connectors, APC, have insertion loss values of less than 0.2 dB and return loss values of greater than 55 dB. Reliable operation of connectors depends on the proper geometry of the convex polished ferrule end face. Connector parameters should be routinely checked by interferometric inspection and include radius of curvature, apex offset, fiber projection, undercut, and polishing angle. A connector is installed onto the end of each of the two fibers to be joined. Single-mode connectors are generally factory installed to meet requirements for optical performance and long-term reliability. The junction is then made by mating the connectors to each side of an adapter, which holds them in place, bringing the fibers into alignment. The adapters are housed within a termination panel, which provides a location to safely house the adapter-connector terminations and allow easy access to installed connectors. Fiber termination panels typically house from 12 to 144 terminations. Termination panels should adapt easily to any standard style of connector or adapter. This allows easy future growth and also allows more flexibility in evolving network design. Fiber cable management within the termination panel is critical. Cable management within a termination panel must include proper bend radius protection and physical routing paths. The fiber should have bend radius protection along the route from the adapter port to the panel exit location. The path the fiber follows in getting to the panel exit should also be very clear and well defined. Most cable management problems in termination panels arise from improper routing of patch cords, which can make access to installed connectors very difficult and can cause service-affecting macro bends on adjacent fibers. Connectors should also be removable without the use of special tools, which can be costly and easily lost or left behind. Proper fiber cable management in the termination panel improves network flexibility while reducing operations costs and system reconfiguration time. When fiber is used in the local serving loop, such as in hybrid fiber coax networks or fiber-fed digital loop converters or DLCs, backup fibers run to the optical network unit, ONUs, or to the DLCs. These fibers are provided in case a technician breaks the active fiber or damages the connector during installation and maintenance. In the event of such an occurrence, the signal has to be rerouted from the original active fiber to the backup fiber. This rerouting is done at the OSP termination panel within the ODF. While the fiber appearances on the termination panel are generally located either adjacent to each other or within a few terminations of each other, this reconfiguration should not jeopardize the integrity of the other installed circuits. If installed fibers must be moved in order to access the target connector, then the probability of inducing a bending loss in those adjacent fibers is increased. And that loss could be enough to provide a temporary service outage. These effects are especially pronounced in CATV systems in which the system attenuation is adjusted to an optimal power level at the receiver to provide the best picture quality. Enabling easy access to individual terminations without disturbing other fibers is an important feature of a termination panel. Reliable optical networks require clean connectors, so before any connector is mated to another, both connectors should be properly inspected, then cleaned if required, and inspected again before mating. Dirty connectors are the biggest cause of increased back reflection and insertion loss in the channel. A dirty ultra-polished connector with a normal return loss of greater than 55 dB can easily have 45 dB reflectance if it is not cleaned properly. Similar comparisons can be made with angled polished connectors. This can greatly affect system performance, especially in CATV applications where carrier-to-noise ratios, CNRs, are directly related to signal quality. In order to ensure that both connectors are properly cleaned, the termination panel must allow them both to be easily accessed. This easy access has to be for both the patch cord connector and the equipment or OSP connector on the backside of the termination panel. Accessing these connectors should not cause any significant loss in adjacent fibers. Without easy access to connectors, technicians will take more time to perform their work, delaying implementation of new services or redeployment of existing services. Dirty connectors can also jeopardize the long-term reliability of the network because dirt and debris can be embedded into the end face of the connector, causing permanent performance-affecting damage. Before we continue further in this lesson, we need to visually see the result of contamination on the end face of the fiber connectors. It is not only contamination on the fiber core that is important. Debris elsewhere can also cause problems because when you mate two connectors together, the particles, especially larger ones, are very likely to explode as the pressure is applied to them. This graphic shows an image of the end face of a connector that had some fairly large pieces of debris on it, taken using a 400 times microscope. Watch what happens as the connection is made using a clean fiber connector and then remated several times. A lot of the debris is spread everywhere like shrapnel on each mating. There is no pattern to where it's moved. But notice that debris at the beginning was not on the core, however it now shows up on the core where it will prevent the transmission of light. In addition, large particles can create barriers or air gaps between the connectors that prevent contact and therefore affect performance. Small particles tend to embed themselves into the fiber surfaces, creating damage to the connector end face. The result here is that we now have two dirty connectors, and if the connector that was being inserted was a test cord, that dirt will now be taken to the next connector that is about to be tested. Connector cleaning prior to patching is essential, and this message needs to be given to anyone involved in patching fiber equipment. Most ODF systems encounter cable management problems in the storage of excess fiber cable. Since most single-mode connectors today are still factory terminated to a patch cord of a predetermined length, there is always some excess fiber remaining after the connections have been made. At some point during the life of the fiber network, it is likely that virtually every fiber circuit will be reconfigured. For most circuits, the duration between reconfigurations will be long, perhaps 3 to 5 years. During this time, these fibers need to be properly protected to ensure they are not damaged during day-to-day network operations. As the fiber's physical length and its potential exposure to damage and bend radius violations is greatest here, the slack storage system is perhaps the most critical element in terms of network reliability and reconfigurability. The slack storage system needs to provide flexible storage capacities, permanent bend radius protection, and easy access to individual fibers. Slack storage systems come in many styles and configurations. Many systems involve coiling or wrapping fibers in open troughs or vertical cableways, which can increase the probability of bend radius violations and can make fiber access more difficult and time-consuming. The accessibility and thus the amount of time required to reconfigure the network is optimal in a system that maintains a continuous non-coiled or twisted routing of fibers. As single-mode connectors become more reliable and easier to install in the field, some of the need for slack storage will disappear. It is also true, however, that terminating the connectors in the field while reducing the initial ODF purchase price will increase the installation cost and time. In existing offices, there will be a substantial base of installed fiber that will require storage for life, unless it is all replaced, an unlikely event due to high cost. The ODF system used should have an effective slack storage system that is easily incorporated or can be omitted, depending on the current network requirements and configuration. When working with intra-facility cables or IFCs, the following factors must be taken into consideration to ensure the best possible performance and ease of maintenance. Bend radius. For cables with load, it is necessary to maintain a bend radius that is 20 times the diameter of the cable jacketing. However, if no load is on the cable while tied down, you are able to maintain a lower 10 times bend radius. Strain relief. Always use the recommended cable clamp as well as properly sized grommet inserts. Lacing. CommScope recommends wax lacing, which makes it easier to manage tension and reduces microbends. Tie-off. Installers should always use some type of insert for protection between lacings and the cable jacketing. Segregating. Because of weight issues, CommScope also recommends separate racking systems for fiber cables and copper cables. The other means of joining two fibers is a splice. Splicing in fiber optics is the physical joining of two separate optical fibers with the goal of having 100% signal transfer. Splicing connections are meant to be permanent, non-reconfigurable connections. There are two basic splicing methods in use today: mechanical and fusion. Mechanical splicing involves the use of an alignment fixture to bring and hold two fibers in alignment. Mechanical splices typically give insertion loss values of less than 0.15 dB with return loss values of greater than 35 dB and involve the use of an index matching gel. Fusion splicing uses an electric arc to weld two fibers together and typically have insertion loss values of less than 0.05 dB and return loss values of greater than 70 dB. Whichever splicing type is used, the ODF needs to provide a location to store and protect the splices. Splicing can be performed on the ODF, on-frame splicing, or in a location near the place at which the OSP cables enter the building, such as the cable vault, off-frame splicing. We will discuss on-frame versus off-frame splicing later. In either situation, the splice enclosure or panel provides a location to store all splices safely and efficiently. The individual splices are housed within a splice tray, generally holding between 12 and 24 splices. The splice trays, in turn, are housed within a shelf or enclosure that can hold anything from 96 up to 864 splices in a single unit. For these enclosures, the most critical fiber cable management features are the bend radius and physical protection. The fiber cable management determines the ability to reconfigure or rework any splices. In routing fibers between the enclosure or panel entrance point and the splice tray, enough slack should be provided and made easily accessible for the technicians to perform any necessary re-splices. Each splice tray needs a sufficient amount of slack fiber stored around it to allow the tray to be easily moved between 1 and 3 meters from the splice panel to ensure that the splice technician can do any work in a proper position and work environment. If the access to the service loop for the splices is difficult, not only will the on-site time of the technician be increased, but also the possibility of potentially damaging another fiber as well. In the splice trays, proper bend radius protection also needs to be observed. Aside from the points mentioned previously regarding fiber breakage and attenuation, a sharp bend within the splice tray near the splice will put added strain on the splice, increasing the possibility of a failure in the splice, but also could cause increased attenuation such as a macro bend. Fusion splices have a higher probability of failing if added stress is put on the splice by a sharp bend before the splice. As networks grow and technologies change, the ability to add optical splitters, wavelength division multiplexers, WDMs, optical switches, and other optomechanical products to the ODF becomes more important. These devices should be easily, safely, and economically integrated into the ODF. Optical splitters are used in CATV networks for serving multiple nodes from one transmitter, greatly reducing system costs. They are also used in local and long-distance networks for non-intrusive network monitoring and work by allowing an active signal to be monitored without interrupting or rerouting service to any spare facilities, greatly reducing the time required to perform testing procedures and troubleshooting. Wave division multiplexers, WDMs, are being used to increase the bandwidth of installed OSP fiber. For example, a 16-channel dense wavelength division multiplexer, DWDM, can increase a single fiber's bandwidth capacity 16-fold. WDMs can also be used in conjunction with optical time domain reflectometers, OTDRs, to perform out-of-band testing on one wavelength, operation on another, on active fibers. The use of OTDRs for out-of-band testing allows for very fast and efficient troubleshooting of fiber networks, as well as the ability to detect problems before they become service-affecting. Optical switches can be incorporated into the ODF for use in redundant path switching, allowing for fast rerouting of critical networks onto spare facilities without having full redundancy built into the network. Fiber optic test equipment can also be housed in the ODF to allow technicians easy access to equipment and test lines. Housing the test equipment in the ODF can reduce the time required for network troubleshooting and restoration. Where to locate optical components such as splitters and WDMs has been debated since their introduction. In the past, splitters and WDMs were often housed in splice trays or at the back of termination panels, but putting these components in splice trays increases the cost of installation, the time required to turn up service, and the probability of the device's failure or damage to adjacent fibers. Today, deciding where to house optical components should be based on cable management and network flexibility. For fiber networks incorporating DWDMs or coarse wavelength division multiplexers, CWDMs, the scenarios become more convoluted. The location of the DWDM or CWDM component depends on the type of system being implemented and how the office is set up. For example, an active 16-channel DWDM system will include signal reproduction at the proper wavelength, multiplexing, monitoring, and regeneration, 16 fibers in at any wavelength and 1 fiber out with the proper wavelengths multiplexed on it. This type of system will be housed in a single rack or cabinet with a single fiber being routed to the ODF. If, however, the system is one in which the transmitters located at different points within the office are operating at the proper wavelengths for multiplexing, then locating the DWDM multiplexer and the demultiplexer passive components in the ODF may make sense. Whatever the optical components or the means by which they are incorporated into the fiber distribution system, they need to be properly protected. Bend radius protection and physical protection are the most important considerations for these devices. Following proper fiber cable management practices in incorporating these devices will reduce the cost of network installation and network reconfigurations. When configuring an ODF, one of the first considerations is the decision between interconnect and cross-connect architectures. As with the location of optical components, this decision has large implications for the network's future growth, reconfigurability, cost, and reliability. Interconnect systems involve the OSP cable being spliced to a pre-connectorized pigtail, which in turn is terminated to the back of a termination panel. The front of the panel allows access to the OSP fiber via a patch cord that is routed to the ODF directly from the FOT equipment. In an interconnect, the FOT fiber does not have a dedicated port location. When the distance between the ODF and the FOT equipment rack is great, more than 5 meters, reconfiguring the network can be difficult. If the patch cord routed from the FOT and the ODF is too short to reach the far end of the lineup, another patch cord may have to be run between the ODF and the FOT. In large office applications, this can take between 20 minutes and 2 weeks, depending on the layout of the office, the state of the cable raceway system, and the availability of a long enough patch cord. Also, any time a patch cord and corresponding fiber are moved, damage can occur. And if the patch cord is damaged during the rerouting, a new patch cord will have to be installed. These situations increase the time required to turn up new services or to reconfigure or restore existing services. This also increases network operating costs and can adversely affect customer service. In interconnect systems, the slack storage system is generally not thoroughly considered, exposing large numbers of fibers to potential macro-bending problems. Bend radius violations are common and individual fiber access can be difficult. The introduction of field-terminated connectors would eliminate any storage issues, but it would also mean that any network reconfiguration would require a new patch cord to be run between the ODF and FOT equipment. This would increase the congestion in the cable raceway between the frames, since the existing fibers would more than likely be left in place. The time required to reconfigure the network would also increase. If no network reconfiguration is anticipated, an interconnect architecture can work. However, as network requirements change, the ability to reconfigure the network effectively and efficiently becomes more important. The fact that the FOT patch cords don't have a dedicated termination location makes patch cord labeling and record keeping both more difficult and more critical. Interconnect generally works best in low fiber count, less than 144 fibers systems, in which the distance between the ODF and the FOT equipment is short. Interconnect can also be more cost-efficient in initial installation, requiring a minimum amount of equipment and floor space. But the more the network changes, the more desirable a cross-connect architecture becomes. A cross-connect ODF architecture provides a dedicated termination point for both the OSP fibers and the FOT equipment fibers. The OSP and FOT fibers are connected via a cross-connect patch cord routed between the two ports on the front of the ODF. This makes accessing the network elements much easier and more cost-efficient and improves the long-term reliability of the installed fiber network. A cross-connect configuration provides the greatest flexibility when it comes to future network reconfigurations. If a reconfiguration is required, all the work is done from the front of the frame, with a patch cord that is generally less than 10 meters in length. If by chance this cross-connect patch cord is damaged during handling, another patch cord can be easily used to replace it. This is not the case within an interconnect network where the patch cord being rerouted is connected to FOT equipment that may be on the other side of the office. Additionally, having proper slack storage for the cross-connect patch cord will ensure that the network can be quickly reconfigured without inducing attenuation on adjacent fibers. An ODF system with a strong, flexible slack storage system will require keeping only a few standard-length patch cords in stock for use in cross-connect routings rather than multiple different lengths. Using a cross-connect architecture also allows multi-fiber cables to be routed between the FOT and ODF, as this can not only reduce the total amount of time required to install the fiber network, but also provides additional protection to the fibers being routed. There are, though, operational and economic disadvantages to using multi-fiber cables in both interconnect and cross-connect applications. For example, a rack of FOT equipment may handle equipment using a certain number of fibers in a multi-fiber bundle. If in 4 years that equipment is obsolete and replaced with equipment that has fewer terminations in the same frame, so the excess fibers will be very difficult to redeploy. The key factor when considering cross-connect and interconnect architectures is the future reconfiguration capability of the method chosen. As the network grows and evolves, new and different technologies will be incorporated into the FOT equipment frames, and the existing equipment will become obsolete or will be redeployed one or more times until the oldest equipment is discarded or all fibers are used. This network reconfiguration could involve moving large amounts of electronics and many long patch cords or reconfiguring short patch cords on the front of the frame. The ease with which equipment is integrated into the network and its potential effects on the installed network will depend on the fiber cable management system. A cross-connect system with proper cable management features will allow the FOT equipment within the fiber network to be redistributed simply by rerouting patch cords on the front of the ODF. Additionally, with cross-connect, both the OSP and FOT terminations have dedicated permanent locations on the ODF. This means that even if the record-keeping for a cross-connect patch cord reconfiguration is not properly done, the technicians will always know where the equipment terminations and the OSP terminations are, therefore greatly reducing the time. The initial installation of a cross-connect system is about 40% more expensive than a comparable interconnect system because more equipment is needed. It will also require between 30 and 100% more floor space depending on the configuration, since there are more terminations required in the ODF network. In most OSP fiber networks, 50% of the fibers are spare or backup fibers, 2:1 OSP to FOT ratio. These fibers are routed in the same sheath as the active fiber, but are used if the connector or the fiber at the far end is damaged. Reconfiguring the network to use the spare fibers is done at the ODF termination panel. Using a cross-connect in this type of configuration will result in roughly a 35% increase in equipment costs, but will provide the ability to reconfigure the network easily while increasing network flexibility and reliability. That completes Part 2. Please continue on to Part 3. Thank you.